Let's do some difficult math because I'm bored. So, I was online browsing for difficult math problems when I came across one that I couldn't solve. It was find all primes p and q to the equation p cubed minus q to the power of 7 is equal to p minus q. I want to thank Prime Newtons for providing this question. I found this question because of him. Now, I saw his video and his solution, and while I was able to understand it, it was a little confusing at parts, and I don't think it's immediately intuitive, so I searched for a better solution, and luckily, after engaging with the YouTube community, I was able to find it. So I'm going to provide you the solution to this question that I myself was not able to solve. So, first of all, you should be able to recognize that this is actually a very good question. And how do we solve it? Well, the first thing I'm going to do is I'm going to manipulate it a bit. So, p cubed minus q7 is equal to p minus q, so that's the original question. And you can actually switch it to, so like this is the same thing, p cubed minus p is equal to q7 minus q. And since p and q are both primes, it's obvious that p and q both have to be at least 2, since they are primes. Okay, so, like I said, we'll get to this, this use of this later. Now, the second thing you want to do is, you want to see, can p equal q? And let's just see that. So, that's p cubed minus p to the power of 7 is equal to 0, you know, because p minus q. So then p cubed minus p7, so p cubed 1 minus p to the power of 4 is equal to 0. P cubed is equal, if p cubed is equal to 0, then p is equal to 0, and p is equal to 0, and if 1 minus p4 is equal to 0, then p is plus or minus 1. As you know, these are not primes. 0 and 1 are not primes, so these are not acceptable answers, which means that p cannot equal q. Alright, so now let me show you something. I'm going to show you that p is actually greater than q squared, and here is the proof. I'm going to prove that. So what you do here, so p cubed is obviously greater than p cubed minus 1. And since p is at least 2, this is obviously greater than p cubed minus p. And this is equal to q to the 7 minus q. Q to the 7 minus q, you can factor out a q, so that's q to the power of 6 minus 1. And since q is at least 2, we can say that this is strictly greater than q to the power of 6 minus 1. So, therefore, we have indirectly proved that p cubed minus 1 is greater than q to the 6 minus 1. I'm going to throw it in for, so p cubed minus 1 was right here, and q to the 6 minus 1 was right here. Take out the negative 1 on both sides. P cubed is greater than q6, and since both sides are positive, you can take the cube root. So then of both sides, so then you get p is greater than q squared, and we have proved what we claimed earlier, and this also automatically implies that p is greater than q. This will be these will be helpful for us later. Okay, so now we got that part done, and what I want to show you next is that primes. Let's find the value of what primes are. Let's find the overall domain of what our answers could be. So you know they're 2, 3, 5, 7, 11, 13, ... You get the idea. And what you notice is that aside from 2 and 3, all of the other primes, 3 and 5, 5 and 7, 11 is a distance of 4, but 11 and 13 is plus 2. So, aside from 2 and 3, all other primes have a minimum distance of 2. So, what I want to check is if the value's 2... Okay, so since P is greater than Q, let's see if P equals 3 and Q equals 2 is a solution. I should have wrote since P equals Q in the beginning, but yeah. So let's see if it's right. So P cubed, let's see, P cubed minus Q7 is equal to P minus Q. So P is 3 and Q is 2. So 3 cubed minus 2 to the 7 equals 3 minus 2. 3 cubed is 27, so 27 minus 128 is equal to 1. Well, this is clearly not true because this is a value of negative 101, and this is a value of 1. So since this was not a valuable solution, P, the minimum distance of these two primes is Q plus... Actually, you know what? I'm going to write it on the... I'm trying to save space, so I'm going to write it on the other side. So, yeah. So, since we found out that this was not a solution, the minimum distance of these primes has to be 2. So, P is at least Q plus 2. Okay. Now, let's go back to our manipulation of the equation. P cubed minus P is equal to Q7 minus Q. Okay, so let's factor both sides. So P squared minus 1 is equal to Q6 minus 1. And there is a principle called Euclid's lemma. I'm going to write it down for you. Euclid's lemma basically states that if a prime P divides the product of AB, then P has to divide at least A or B. So what that looks like on in notation, mathematical notation, is if P divides AB, then P divides A or P divides B. So using Euclid's lemma, we have here P divides Q or P divides Q to the 6th power minus 1. Now, obviously, P cannot divide Q because remember, P is greater than Q. So therefore, P has to divide Q to the 6th minus 1. So, yeah, by default. So I'm going to erase most of this whiteboard except for the question. So just take a screenshot of this if you want to track this down. Okay, so P divides Q to the 6th minus 1. And just for that manipulation of the equation, I'm just going to write that here really quickly. Okay, so P divides Q6 minus 1. Now, Q6, I'm just going to do this on the side. Q to the 6th minus 1 is equal to Q cubed minus 1 times q cubed plus 1. I know this personally because I've done this for a very long time, so this is on the side. I'm just going to quickly mention this. A cubed minus 1, don't worry about A is any kind of number, is equal to A minus 1, A squared plus A plus 1. And A cubed plus 1 is equal to A plus 1, A squared minus A plus 1. Okay, so this is equal to, and so this is equal to q minus 1, q plus 1, q squared minus q plus 1, and q squared plus q plus 1. Okay, so this means that P has to divide one of these four products. P has to divide either q minus 1, q plus 1, q squared minus q plus 1, and q squared plus q plus 1. One of these four. Okay, well, because earlier we have shown because P has to be at greater than or equal to q plus 2, but that eliminates q minus 1 and q plus 1. Also, because P is greater than q squared, as seen earlier, well, P is greater than q squared, but because q is at least 2, that means q squared is greater than q squared minus q plus 1, which then implies that P is greater than q squared minus q plus 1. No, sorry. Which implies that P is greater than q squared minus q plus 1. So, as a result, P cannot divide q squared minus q plus 1. So, therefore, by default, P has to divide q squared plus q plus 1. Now, here's the thing. So, P divides q squared plus q plus 1. So the maximum value of P is q squared plus q plus 1. But if P does not equal to q squared plus q plus 1, then P would have to equal q squared plus n, since P is bigger than q squared, where n has a value between 1 and q plus 1. Okay, but then if this was true, this would imply that P divides q squared plus q plus 1 minus q squared plus n. Because if P is equal to q squared plus n, then P also divides q squared plus n. And this would mean, so if you do the subtraction, P divides q plus 1 minus n, which is clearly less than q. So, q plus 1 minus n, P is clearly bigger than this because P is bigger than q, right? So if p is bigger than q, then p is bigger than q plus 1 minus n, which is a contradiction. This is not true. So as a result, p has to equal q squared plus q plus 1. So take note of this. Once again, I am going to erase the whiteboard. Okay, so as mentioned, p is equal to q squared plus q plus 1. So we can plug this into our original equation. So let's just do that. So p cubed minus q7 is equal to p minus q, q squared plus q plus 1 cubed minus q7 is equal to q squared plus q plus 1 minus q. I'm going to fast forward this simplification process because this part is very boring. Okay, so when you simplify it down, you get q to the power 7 minus q6 minus 3q5 minus 6q4 minus 7q cubed minus 5q squared minus 3q is equal to 0. Obviously, q cannot equal 0. So then all you have left is q6 minus q5 minus 3q4 minus 6q cubed minus 7q squared minus 5q minus 3 is equal to 0. And then, as you learned in grade 12, you look for factors of the constant term, which is negative 3, and that's just plus or minus 1 and plus or minus 3. Now, because q is prime, the only candidate factor for between these four choices is q equals 3. So try q equals 3. And I'm not going to try it. I already tried it. You can see for yourself. But when you plug q of 3 into this long equation, it equals 0. So q equals 3 is a solution. And if q equals 3, then p equals 3 squared plus 3 plus 1 equals 13. So therefore, the only solution to this question, p cubed minus q7 equals p minus q, is p equals 13 and q equals 3.